the webinar, so this recording will be available on our website in case there's anything you want to go over again. And without further ado, I pass over to Nicole. I'm very looking forward to hearing your talk, Nicole, and welcome and thank you.
Okay, thank you, Michael, and thank you also for inviting me to this webinar, and welcome to everybody who's today attending this webinar. For me, it's a great pleasure to be here and to present you today our current work on students' mechanistic reasoning. And before going deeper into the complexity of mechanistic reasoning, I would like to introduce you to my current research group, so that you know all the people that do the work. And I want to mention especially Ira Kaspari, who's on the right side of the slide, because I will talk a lot about her PhD work. And in the last year, she put an incredible amount of effort and time in this project. So this is her work. So what are we going to discuss today? This is the outline of the webinar. So first of all, I want to talk about our goal and approach, so how we translate aspects of the philosophy of science to organic chemistry. Then I want to give you an overview about a quantitative study that focuses on students' use of explicit and implicit properties. And then in part 3, we go a little bit back into the theory, and we will see a case for two different accounts. So it's based on the philosophy of organic chemistry. And then we apply this on analyzing students' mechanistic reasoning. In part 5 of the webinar, we'll focus on teaching, and we tested a small scaffold that might help students to consider multiple variables. So this is the plan for today. So when you think about I'll just have to wait. When you think about difficulties that students have in organic chemistry, there have been a lot of research going on in the last decades that focuses on the problems and the difficulties that students face when learning mechanisms or working with representations. So here's just a short summary of several of studies. So this is not a complete list, but just a short overview. So we know that students focus on surface features when dealing with typical mechanisms and representation that we use in organic chemistry. And they do not often attribute the appropriate meaning to the symbol. For example, the electron-pushing formalism had been the topic of various investigations. We also know that students use general heuristics when solving problems, which are not often based on a chemical knowledge, but rather on something like familiarity with molecules. But Sharia and co-workers have described different types of reasoning strategies that students use. For example, that they tend to use rule-based reasoning instead of a more sophisticated model-based reasoning. And Weinrich and Sevian in 2017 have shown that students with higher level of abstractness generate more plausible solutions. So we have evidences for difficulties that students have, but also evidences for what makes them possibly successful in solving mechanism tasks. But when we want to discuss about, well, when you discuss mechanistic reasoning, I was always concerned with that question: how can we describe what constitutes mechanistic reasoning? And during my postdoc time, I came across a paper from Ross and Hammer, who used the philosophy of science to generate codes to describe how primary school kids conceptualize mechanisms. So this was the first approach to start in that area and ask myself that question, and that is also the leading question of the project. So on the next slide, I want to show you, when it's uploading, our approach. So we would call that a subject-oriented perspective on mechanistic reasoning. So we use a lot of work in the philosophy of science and in the philosophy of organic chemistry to find how they conceptualize mechanism and reasoning with mechanism, and then we use this as a lens to analyze what students are actually doing when reasoning with mechanisms, kind of to analyze students' productive resources in order to find the gaps that we can fill in teaching. But on the other hand, also, the subject perspective helps us to guide a teaching experiment, for example, to scaffold students' reasoning. And we will cover all the three aspects today in the webinar. So when we think about a subject-oriented perspective, then we think about what is actually the subject of organic chemistry, which is the mechanism, and also we think about the questions of the discipline that shapes our reasoning. So we have the two different parts. On the one hand, the components part, which is the answer to the question, what is the nature of a mechanism, which components are used in reasoning, and on the other hand, how to connect components in reasoning about mechanisms. So we will focus on these two parts that constitutes our subject-oriented perspective. First of all, I want to focus on the left-hand side on the components, and I will introduce you to work that's been done in the philosophy of science, and especially in the research group around Mahamardhan and Craver. And they were researching or investigating what actually constitutes a mechanism in the natural sciences. So they were not explicitly focused on organic chemistry mechanism, but neurobiology and astrophysics. And they are saying that mechanisms are composed of both entities with their properties and activities. Activities are the producers of change, and entities are the things that engage in activities. And activities usually require that entities have specific type of properties. So Mahama and co-workers adopt a rather dualistic perspective on the main components that constitutes a mechanism. They're also talking about other components, but today we will just focus on entities and activities. And I will show you in the following how that translates to organic chemistry. And the slide is uploading. So when we think about entities and their individuating properties, we started to define what constitutes explicit properties and implicit properties. Explicit properties are all these recognizable features of a structural representation that characterizes an entity. For example, information about connectivity, information about charges, or elements in a molecule. So these are all the explicit properties. The implicit ones are those who are non-recognizable features of a structural representation. Those are not often expressed by the representation. For example, the orbital size or the electron density of molecules. So we have these different types of properties, explicit and implicit one, who characterizes entities. So this is how we translated the idea of entities and their property that Mahama described in the philosophy of science into what does it mean in organic chemistry. And then we have the other part, the activities. And the activities expresses the change. So activities are the dynamic part of a mechanism. And as we all know, entities are the things that change in a process or in a chemical process. So activities describe how properties of entities change in a process. So it's information about bond cleavage, bond formation, and also formation of charges. So in order to reason with these two main components of a mechanism, a learner needs to know how to appropriately describe these components, the changes as well as the entities and their properties. And in the following, we were interested in how students deal with, specifically with the entities and their property. And this leads us to the next study that I want to show you, or that we want to discuss now. And now it is uploading. I'm sorry for that slow change in slides. So we focused in an exploratory quantitative study on students focused on implicit and explicit properties of entities, just to know how they are engaged with these two different types of properties. And I want to show you again an example how we come to our research question. So when you have that typical molecule here, and again, we have the explicit properties that characterizes the entity, and on the other hand, we have the implicit properties that characterizes the entity implicitly. And when we ask then a question to the molecule, decide which two alcohol functions react similar with a base, students can answer that question in the following way. So he might mark the two alcohol functions on the aromatic system, but when he's doing that, as a teacher, I might not know if he has thought about the implicit properties about the acidity of the two alcohol function, or if he's just choosing the two based on explicit properties that are recognizable on the surface level. So this was the starting point for the research question that we had going into the quantitative study. So do students actually recognize implicit properties of entities in items which differ in their supporting or distracting explicit properties? So this was the assumption that we had, and for that we created different items that we wanted to test. So here are the two different type of items that we were focusing on. We used SN1 and SN2 reaction and created items in the different concept categories that are necessary to understand SN1 and SN2 reaction. Here are the two examples, leaving group and nucleophilicity. When you look at the first item type, the supporting explicit property item type, and you see the prompt indicate the two structures that would react similar in a substitution reaction, you can see that choosing the correct answer here, B and C, is supported by also an explicit similarity between the two halogens. So this is an item that does not allow to really assess the ability of students to infer the implicit property. On the right-hand side, for the nucleophilicity, you see an example for a distracting explicit property item type. Because here, the correct answer to choose the nucleophile or the two nucleophiles that would react similar in a substitution reactions are A and B. And they do not share any explicit property besides the negative charge. But the negative charge is shared by all the three molecules. The distracting explicit property is here the negatively charged oxygen. And with these two type of items, we then went into our study, and I will give you a short overview about the study design. It was, as I said, a quantitative one, so we did the study with 150 chemistry majors and student teachers at German universities. It was our first year of organic chemistry and right before the exam, so hopefully they have learned. We had two parts in our instrument. One was just a multiple choice, and the second part was just multiple choice and elaboration. So students were asked to elaborate on their choice. I will not focus on the elaboration part today. I will just give you an overview about the answering pattern, the box plots that we had from the two different items, and I have to refer to the manuscript that will hopefully be online at some point this year for the elaboration part. So when we look at the results, when we compare the different types of items, so the supporting item and the distracting item, we can see there's a large difference between the answering patterns that we found in the study. You can see the students have no problems or not so many problems with answering the supporting items correctly. But when we look at the distribution of answers for the distracting items, you can see that it's quite lower than for the supporting items. So we have a large significant effect, and the Cohen's d-value from 1.5 also shows a large effect size between the two different type of items. So this was on the one hand not quite surprising, but the effect size and the difference between the two items was the one thing that surprised me the most, because when we think about mechanistic reasoning and we want that the students are able to use the components, here the entities and their properties, it's crucial that they are able to recognize implicit properties in various structural settings, not only when when two implicit properties are supported by an explicit property. So this is something that kind of adds to the research on mechanistic reasoning. A colleague of mine and I were publishing in 2018 a paper on contrasting cases, because all the research kind of inspired us to propose different type of tasks that we can use in organic chemistry to help students think more about implicit properties in various structural settings. What you can see here on the right side is it's not something statistically or so. It's just I wanted to show or visualize what the difficulty could be with the different type of concepts that we use in SN1 and SN2 reaction. When you look at the degree of branching, which is just focusing on tertiary, secondary, or primary carbons or carbocations, or at solvents effect, then you have the case that often explicit properties of entities matches implicit ones. So as a student, I don't really need to go on the implicit level to make any judgments. I can just count substituents for the degree of branching. This is different when we go to leaving groupability or nucleophilicity. In those cases, the explicit and the implicit property do not match in all cases. So not every nucleophile or not every molecule who has a negative charge is a nucleophile. So this is just how to visualize or to remind us as teachers also that that the concept that we use for substitution reaction is also different in their complexity. So with this being said, you see that small time for discussion part here in the left-hand corner. So at this point, this could be a good moment to ask questions for that first part of the webinar.
Thank you, Nicole. So yes, if anybody does have questions, feel free to post them in. One thing that struck me was the sense that students are relying on explicit properties. And I'm wondering, from the point of view of teaching, how do we, I suppose, force them? I mean, you have devised questions which really tease out whether or not they really understand implicit properties. Is that something that could be incorporated much more into teaching if we really feel they should rely on implicit properties? Can we consider teaching approaches or assessment approaches that focus more on the requirement to look at implicit properties?
Yeah, I mean, as I said, or we try with our paper that we published in JCE this year to propose a different way of how we use tasks in organic chemistry, kind of to force students to always go to the implicit level and not to rely too much in their argumentation on the explicit properties that they can normally see. And what you mentioned with the teaching is also the question of assessment, because when we think of normal assessment items that we use in organic chemistry, it might be those kind of items that I showed you for the quantitative study. We have to think about what are we actually measuring with those items. So when we want to really assess conceptual understanding, I should really focus on items that do measure their conceptual understanding and not only recognition of explicit similarities. And this could also be an hint for how I can create exercises or tasks in teaching, always to change the structural context or the structural setting in which I have to work with implicit property, kind of to force students to always go beyond that level. Not always show two halogen as leaving groups, but maybe to compare a tosylate and a chloride, and then to think what do they have in common, although they're not similar on the explicit level, but what type of implicit properties do they share?
Great. Okay. To the audience, I've just realized that I hadn't got the chat button turned on, so that may be why you weren't able to ask a question. So what I suggest, Nicole, is that if you continue on with the presentation, and we can pick up questions on this part as well as later parts. So I'll let you continue now with the presentation.
Okay. Yeah, we can do that. So I was just change the slide to part 3 of the webinar. And now I want to show you how we use the philosophy of science to make a case for 2 different accounts. That sounds maybe quite a little bit complicated, but we'll see in a minute. So at the beginning, we were focusing on the components. So we're focusing on entities and the properties. And now I want to switch a little bit to the part of the reasoning. So rather, what type of question does the discipline tries to answer, and how can we reason with the components to answer those questions? So we focus on the reasoning part. And when we come from a subject-oriented perspective, then we have the discipline in mind and the goal that organic chemistry has, which is to synthesize highly selective products. And though the discipline is concerned with these 3 types of questions, or I mean multiple questions, but of that type. For example, why do reactions of type A proceed faster than type B? Why do reactions of type A have the products B and C? Or why does reaction A proceed by pathway C and not D? And when we look at those questions that are typical questions in the discipline from an educational perspective, these are all questions of case comparisons and relations. So I will show you an example how we try to answer a typical question of that type. So here we have a reaction, and the question for that reaction is why which proton, A or B, is abstracted faster in an E2 elimination. So it's a question about speed, a question about activation energy. And we use here Goodwin and his work in the philosophy of organic chemistry, because he's saying that answering such a typical question requires 2 different accounts, an energetic one, which is a claim about the energy, and a structural account, which is a claim about the structure. And the direct answer to that question about the activation energy is to make an energetic account, or to make a claim about the energy. And for our case, for the abstraction of the proton A or B, we can say that the activation energy for the abstraction of proton E on the energy surface is lower than for proton B. So this could be the direct answer to the question, but we need a structural account to justify why we can make that energetic claim about the difference in activation energy. Well, here's where the structural account comes to play that Goodwin also describes. And it's a little bit more complicated than just saying which is lower on the energy surface. So when we generate a structural account, this is an act of, I would say, converting explicit properties or explicit property differences, then differences and implicit property of the entities on the change that we observe in the reaction. And the change here is the formation of a double bond. So we have a property change, we form a double bond, so this is why we call it the change. And this can be then afterwards connected to the energetic account. So when we look at the structural account that we can formulate here, we have to think about the transition state, because we ask the question for the activation energy. So the structural account here could be that the transition state of the product determining step for A and B has some double bond character. The hyperconjugative effects on the forming double bond are stronger in A than in B, and thus increase the electron distribution in the transition state. So in the structural account, we have not made any claim about the energy. We're just forming a claim about structure that can then be connected to an energetic claim. This might be a little bit difficult to follow, so I will, on the next slide, summarize how we use structural and energetic account to answer a typical organic chemistry question. So in our structural account, we did the following. So we were looking for structural differences. This is what I said in organic chemistry. We normally answer question of case comparison. So we have here the structural differences, and we have to formulate how the structural difference influence the change of properties that we have in the reaction. Here, the forming of the double bond. And then with the structural account, then we can make the claim about the energy and answer this type of question. We use these two different accounts, a structural account and an energetic account, to inform our qualitative study on students' mechanistic reasons. So we were wondering how students would solve questions about case comparisons. And I will show you in some seconds our research question that we have. So here again on the bottom of the slide, you can see again the structural account and the energetic account, and we had three different types of research questions going into that qualitative study. The first one was, which description of change do students use in their structural account? So how do they describe the change of the reaction, and how do students connect structural and energetic account? The third research question, how can levels of causal complexity within student structural account be characterized? Will not be discussed today, so I have to refer to the manuscript or the publication that will be out hopefully soon, that further illustrates how students verbalize the influence of the structural difference on the change in their structural account. So let's have a look at the study design that you know how we did the study. As I said, it was a qualitative one, so we had 20 students, chemistry and food chemistry major, and we were this time in an Organic 2 course around the exam. Our instrument was here two contrasting cases that I will show you in a minute, and the prompt was to predict the relative activation energy of the contrasting cases. So we choose to ask for the activation energy as our question on the energy. Then we coded the student's description of change and the student's connection between the structural and the energetic account, and also students' causal complexity within the structural account, which I will not talk about today. So on the next slide, you can see the two problems that we use. So both of them are case comparisons. We have two reaction steps, elementary reaction step here, the elimination of a leaving group and the formation of a carbocation. So we reduced our problems to just one mechanistic step. We already did some research on reasoning with multiple steps that was already published, but here for this case, for a structural account, we wanted to focus on how students describe one mechanistic step. And we will focus on problem one today, not to have too many different types of structures, so you can focus really on problem one, and this will be the leading problem that we are going to discuss today. The first question that we wanted to answer is which description of change do students use in their structural account? On the left-hand side, you maybe recognize the different parts of a structural account, structural difference, influence on, and the description of change. When we have our problem one here, the changes that you can observe is, on the one hand, the bond cleavage, the positive charge, and also the negative charge. And these are changes that are typical of a reaction of that type. And today I want to focus on the most prominent change that is normally verbalized when talking about elimination of leaving groups, which is the positive charge. And we were looking at two different ways of how students could describe the change that they observe in a reaction. On the one hand, the static perspective is when they talk about just about the carbocation and about the positive charge, which would be a kind of a product-oriented perspective on change. So they just look at the products. And on the other hand, we have a dynamic description of change. And with dynamic description of change, we mean when students are verbalizing a formation of a carbocation or the formation of a positive charge. Kind of to have that dynamic perspective on the process. I will give you an overall result on how students describe the change in our interviews. We've seen that 3/4 of the students used a static description of the change positive charge, so they were just focusing on the final carbocation, and only 1/4 of the students used a dynamic description of change, of the change positive charge. So they were rather thinking about the process of charge separation and forming of the positive charge. You might wonder why this is important to think about it in a static or in a dynamic way. So I've choose a student as an example, kind of to see how that looked like, how they verbalize a static description of change, and then we can see later on how that influences their connection to the energetic account. So here we have Hannah, and Hannah was coded as a static description, and she referred to the positive charge. So Hannah is saying, and the one is tertiary and the other is secondary. So she's talking about the carbocation here in the product. And basically tertiary is better stabilized because then the positive inductive effect comes from both of the CH3 groups. So I would say this here in the first step has lower activation energy because the product is more stable. And then she further continues and describes what she means with a positive inductive effect. And she's saying, the C atom here, C atom of a methyl group in A, would push electrons over there to the positive charge. And then the bonding electrons between the two would then be localized more on the side of the positive charge C. And so the charge here becomes a bit smaller. So you can see in her verbalization of how she thinks about the carbocation, she's really in a static perspective, so she focuses on what influenced the positive charge in the product, and it's not thinking about the formation of the positive charge in the product. So when we look how she combined the structural account with the energetic account, but before I have to say we asked all the students, and I have to remind you that we asked all the students to make a claim about the relative activation energy. So all the students in our study made any kind of claims about which reaction has a lower activation energy. And here you can see I underlined again what we've had on the slide before, which is Hannah's connection between structural and energetic account. So she's saying, so I would say this here in the first step has lower activation energy because the product is more stable. What she's doing here is an inappropriate connection between structural and energetic account, because she is only thinking about the product and makes a claim about the activation energy, which requires a dynamic perspective on the process, because the final potential energy of the product was not the question of the problem. So, but what we could see here in Hannah and also in some students who made that inappropriate connection between the product and the activation energy was when we continue looking in her interview, the interviewer was asking her, so you sound a little hesitant. And then Hannah started to doubt what she mentioned the slide before. So yeah, because I thought that actually the activation energy doesn't necessarily have anything to do with the thing at the end, well, with where the energetic potential of the product is. So although this might be maybe a positive artifact of the interviews that Hannah and some of the other students started to doubt their connection, it's also nice to see that the students realize that they need a dynamic perspective on the process to make a claim about the activation energy. But only two students, after doubting their connection, made the switch and formulated, again, a dynamic description of change. When we look further in Hannah's case, we could also see that there's a problem between how students think about the representation that we use in a structural account, which are the typical structural formula, and the representation that are common when we talk about energetic accounts. So she's saying here for the positive charge of the carbocation, she's saying actually this means the positive charge is always unfavorable. If the molecules always seek to not to be charged because this is more favorable. So she knows that the positive charge is, as she's saying, is always unfavorable. But later in the interview, she draws the energetic representation of the reaction, and you can see that she's drawing an exothermic reaction. So it's kind of, there's a disconnect between how students verbalize or think about representation in a structural account, and then the connection to how they display or how they draw their idea about the energy of the reaction. So to make a summary of what you've seen in the last slides, we can say that looking at our data, that students engaged in a dynamic description of change made the appropriate connection to the activation energy, and they were not doubting that this is the right way of connecting structural and energetic account. But those students who are engaged in a static description, or rather a product-focused description, often doubted the connection to the activation energy. What this study on students reasoning about this case comparison also reveals is productive resources to combine structural and energetic accounts. So all the students who have that idea about the dynamic in a process, the charge separation and the formation of a positive charge, had no problem to make a claim about the activation energy. So this could be a hint for future teaching to see how can we help students to think in a dynamic way about the processes and not focus too much on the final product or final intermediates of a reaction step. And you can see in the small corner that we have, again, a little bit time for discussion, and I'm happy to answer your question.
Great. Yes, some questions have come in. So if people would like to add questions, you can just use the chat box at the start in the bottom right-hand corner. One thing that struck me was when you were showing Hannah's interview transcript, I understood what you were saying about the carbocation as essentially a static entity, but she did say words like push electrons. There did seem to be some sense of understanding that there was movement. So are you ascribing it static because you were considering only the carbocation, in other words, the product, the intermediate that's being produced?
So when we think about static description, then we mean the static description of change. So in a broader sense, how she verbalized the formation of the positive charge. I mean, you're right when you're saying that she kind of has that dynamic idea of pushing from the CH3 groups to the positive charge, but that's not how what we coded as change. So this is just a kind of a dynamic perspective looking at a static property.
Yeah,
it's kind of hard to explain, but we coded only as static or dynamic how they perceive the change. So if they're talking rather about the formation, or if they rather talk about just, oh, here's the positive charge. So this is what we call then a static perspective. Yeah.
Yeah. And then there were just two questions in about I suppose just the assessment of this in your own practice. So Olivia was asking, do you ask students to articulate these explanations or to construct energy profiles and explain it? And I think this gets back to what you were saying about how do we assess students to really tease out whether they understand these implicit or dynamic representations?
Yeah. Yeah, this is an interesting question, and I have to say that I'm not teaching the class, and we try to talk with the professor of the class, kind of to make sure what they do in their class, and it's an OC2 class, so they have seen some of the energy profile. So, but I can't say that they have specific tasks to let the students really explain what they see and what it means. So I would say you can think of a traditional organic chemistry course that kind of throws in some energy profiles from time to time. And I'm not saying that we blame the students of that disconnect, but it's rather, or it should remind us as teachers that we should really think about to connect those two representations more often. So I can totally understand that the question of Olivia saying that so if they haven't had the experience of working with an energy profile related to what they see at the structural account, then it's hard to combine that. And we see it in students that they have the problem to connect the two. But I mean that was not the main focus of the study, rather how they constructed their structural account. And as far as I know, our assessments in OC2 courses do not include any energy profiles. So they are often give the product, give the mechanism, and such type of tasks.
Yeah. Okay. There's actually a related question, but I have a feeling it's essentially looking at how, so I understand that you're not teaching the course, so this perhaps is a bit unfair, but I think it may come in later in your talk. This idea of how do you scaffold students' approach to these limited ideas, but I think that perhaps is a slightly that may be your next phase. So in other words, you're talking about energy profiles and you're talking about reactions, and you're describing those from a teaching point of view. Naomi's asking, how do you address students' limited ability to consider energy profiles? Is there any glimpse you can offer from your explorations with students, how we might help them promote the consideration of energy profiles?
So far, I have no, I would say, empirical evidences what would be beneficial for the students to connect these two. So the example that we showed here with Hannah was something that kind of came up out of the interview. So we haven't we haven't thought about scaffolding this. So the next part, the scaffold that I want to show you in some minutes, is rather focusing on the structural account and not how to connect the two. But this is definitely a thing that also come up in our qualitative study, to find ways to combine the two more explicitly, kind of to have different types of reactions and then always relate the energy profile together. But as I said, we don't have any empirical evidences or results that I can say that this is helpful or this is not helpful. So this is just something that we have to pursue in the future.
Yeah, well, I think the interesting thing is you are first identifying these issues and telling us that we do need to think about them. And then a final question is just from Jennifer, who just is again about the running of the module. Is this a module that has continuous assessments throughout, or is it just one end of module examination? And she's asking because, of course, there are some sophisticated concepts in here which perhaps need some formative assessment to help students along. So is it formative assessment mainly, or is it an end of module examination?
The OC2 course has an end of module examination. So it's just really pure, simple, traditional OC2 class. And we just went in there and did our study and tried to find out what are the students able to do. So kind of we have that structural energetic account as described by Goodwin, and now we kind of try to see what the students are able to do on their own, even if the class was just a traditional one. So kind of to see what are their productive resources that they can that they use to make the structural account and to connect and then to see what are still the gaps. And not often blaming the students on what they are not able to do, but rather to see what are the positive resources that they can use to deal with these case comparisons.
Yeah, I mean, I think it's that very context which gives your work such value, because you are studying, as you say, the traditional classic organic chemistry course. Okay, I'm gonna turn off my mic and camera and let you continue on with the presentation.
Perfect. Yeah. So the last part now. So we have 50 minutes left. So I want to show you a scaffold that we use to help students consider multiple variables. And when we think of multiple variables, some of you might remember the work that Bhattacharya has done a couple of years ago on thinking about, on investigating how students solve mechanistic tasks, and he demonstrated that students often tend to use single variables in their reason, although there might be multiple variables present that they can incorporate in their decision making. Or they explain properties, for example, the acidity of molecules based on a single property of an entity and do not consider multiple aspects. So this was kind of the idea of how can we scaffold students to consider multiple variables that are present in a task. And as you might, if you remember the problems that we had in the first part of the qualitative study, these are perfect cases to think about multiple variables. So we were adding a small teaching experiment at the end of the interviews that we've done in our qualitative study, because we wanted to know how students reasoning is without the scaffold, and I've shown you this or parts of it on the part before, and we wanted to know how students reasoning change with the scaffold. So does the scaffold actually help students to consider more effects, and how does the reasoning change when using a scaffold? So we have again the same problems as in our large qualitative study. Here's again our contrasting case, and when we think about multiple variables, you can see that we have different structural differences in here. For example, the carbonyl group and the alkenyl group are two differences between the reactants, and then we have in the first reactant we have two methyl group versus one methyl group, and these structural differences can have an effect on the change. So in the following, I want to show you the 4 instructional steps that we use in our scaffold to help students think about the different variables. So the first instructional prompt was to ask students to list all the changes that occur in the reaction step. So an example could be to say it's the formation of the positive charge. So we are already familiar with that change. This is definitely a change that students are using in that part of the scaffold. Then the next step would be to identify different explicit property, kind of to mark, okay, I have a difference between the alkenyl group and the carbonyl group. I have here 2 methyl groups and 1 methyl group. Or you can say it's a secondary versus a tertiary carbon. So it's just important just to note the difference, and that's the second step. In the third instructional step, it's important to explain the effect that each of the structural differences that we identified in step 2 has on the change. For example, how does the carbonyl, for example, the electron withdrawing effect of the carbonyl affects the formation of the positive charge? This could be combining changes that I identified with the structural differences and put them together and formulate an effect that the structural difference has on the change. So with this, you can create multiple arguments. And so in the fourth instructional step, it's important that I weigh the effects, because I want to make a claim about the activation energy. So it's important to weigh the different effects that we have, alkenyl versus carbonyl, and methyl group, the two methyl group versus one methyl group, kind of to make then a final judgment about the activation energy. So let's see how the students were working with a scaffold, if that had any effect on the effects that the students considered to answer their question. So our research question was, does the scaffold help students to consider more effects? And you can see here we have the numbers of students that used 1, 2, 3 effects, one time without the scaffold, and in orange with a scaffold. And you can see that by using the scaffold, you can see that students use use more than just 2 effects. So the numbers of students who use 3 effects increases. So we only have 3 effects in the problem here. I will also show you on the next slide which type of effects increases. And then you can see we have the 3 effects that are important in our problem. On the one hand, the positive inductive effect on the positive charge, the positive resonance effect of the alkenyl versus the carbonyl group on the positive charge, and the electron withdrawing effect of the carbonyl on the positive charge. So these are the 3 effects that you could use to make a claim here about the problem. You can see that only the positive inductive effect and the positive resonance effect increases by 1 student. So we had in each category 1 student who were mentioning that effect with the scaffold. And we have the largest increase in talking about the electron withdrawing effect here in the 3rd effect. This was something that was not familiar to the students. So normally when they think about, or when they were taught elimination reactions or leaving group or departure of a leaving group, then the carbonyl is not something that they see in that reaction context. So it was something that they did not identified as a structural difference and formulated the effect. So this is kind of a nice to see that the scaffold also helps students to think about effects, although they are not familiar with such an effect in that reaction context. But I will go ahead and show you how the reasoning of 1 student, and here we have the case of Marie, changes when using the scaffold and thinking about that case comparison. So she's saying for that problem, well, in A, we have 2 methyl substituents. So she's thinking about the methyl substituent as that structural difference between the 2. And the methyl substituent has a positive inductive effect. And that means it's electron donating, and that's why we can stabilize the positive charge. And well, in A, we have 2 of these methyl substituents, and in B, there's only 1. Because of that, I would say that A has the lower activation energy. So here she's just talking about that inductive effect, and she's not referring to the structural difference between the alkenyl group and the carbonyl group. So she's just focusing on one difference. And then again, Marie approaching the problem without the scaffold, the interviewer was asking then her, is there anything you want to add? So kind of to see if she wants to add any other things that she could identify. And then she's saying, well, I'm still thinking about whether the carbonyl group here also has an effect. Because here we have a CC double bond, here we have a CO double bond, whether this could somehow also have a stabilizing or destabilizing effect. But I won't come to that right now. So I would say that A, well, because of the inductive effect of the methyl group, has the lower activation energy. So she kind of realized that there's another structural differences that can have an effect, or that can have an effect on the formation of a positive charge, but she is not pursuing this difference further in her reasoning. So this was without the scaffold. Now let's look at the scaffold sheet that Mary used in the teaching experiments. Here you can see the different parts that she has to that she had to fill out, and we're now going to follow how she deals with that sheet in the scaffold. So she first identified the change, so it's talking about the carbocation. Then she identifies the two different differences, so two method versus one method group, or tertiary versus secondary, and the other structural difference, CO versus CC. And then she explains the effect between the explicit structural difference and the change. And she's saying the positive inductive effect stabilizes the positive charge. So this is all these steps that has been done here by the scaffold are also the step that she has been done without the scaffold. But now we can see how the scaffold makes a difference for her reasoning about the problem. Because with the scaffold, she could now explain an effect that the explicit property difference CO versus CC has on the carbocation formation. And she's saying two positive charges next to each other are very unfavorable. So she's drawing a resonance structure here of the carbonyl and the positive charge. And so she is able, with the help of the scaffold, to formulate an additional effect that she was not explaining before without the scaffold. But to make her reasoning complete, then we have again the fourth step that the students have to take, the weighing of the effects. So now she was thinking about the difference two method group versus one method group, and alkenyl versus carbonyl. And now she's again, with help of the scaffold, weighing, or tries to weigh the effects. And she's saying, well, if I look at the method substituents, then it would be the activation energy was, according to this, A would be lower. So this was her guess without the scaffold, that A has the lower activation energy. And in the case of the other, well, in the case of the carbonyl and the CC bond, reaction B should have the lower activation energy. So she's kind of switching a little bit. Then the interviewer asking her, how do you come to an overall decision? What do you need to know to come to an overall decision? And then Marie is saying, because I have the two positive charges here, in the case of the carbonyl, that could theoretically be next to each other, this is very unfavorable. So I kind of tend toward B having the lower activation energy. So even with the scaffold, and you can see that the weighing of the effects still causes some problems because they don't know how big the effects are, or about the strength of the effects when they have to weigh them. But she also switched her prediction for the lower activation energy from A without the scaffold to B with the scaffold. So when we summarize that, we can see that when guided by the scaffold and solving this case comparison, the number of effects that students consider increases. We still have problems, or the students had problems in our teaching experiment with the fourth step, weighing of effects. I mean, this is not surprising because it's something that requires experiences in the strength of effects and what overweighs in other effects. But combining contrasting cases and the scaffold seems to be a very promising approach that we will pursue also in our research. So when we do now a final summary, and I see I don't have so many times left, we started with that question, how can we describe what constitutes mechanistic reasoning? And I could show you different things. On the one hand, on the left-hand side of the slide, that reasoning or mechanistic reasoning is reasoning in case comparisons, so always to have reference points, how to relate things together and make a judgment. And we talked about structural and energetic accounts. So how can I make a claim about energy? So I'm using a structural account to justify the claim. And then we've seen students' productive resources, so students' description of change when they do it in a dynamic way. So they can connect this then to the energetic account. So we're talking about students' productive resources. On the right side, I could show you a scaffold that we use. So that reasoning or mechanistic reasoning is also reasoning about multiple variables. And with our scaffold, we could show, or we could support students to consider various effects when solving these case comparisons. And on the bottom of the slide, these are kind of the challenges that we try to face in the future and other research projects. On the one hand, how can we foster students' dynamic perspective on change, so help them to think more about the process instead of the product? And how can we teach the weighing of effects, and what type of instruction is needed to help students to do that step? And with this being said, I would like to close the part, and I would like to thank you again for attending this webinar. And I think that Michael or the audience might have some questions. So if there's time, I'd be happy to answer.
Great. Yes. Thank you very much. We are close to time, but I think there's certainly time for a few questions to consider the last part of the talk. One thing that struck me is the scaffolding at the end. How much of that is raising awareness to the student, or perhaps giving them confidence that something they already knew is a valid reason? I was just struck that the student, in the absence of scaffolding, was tempted to say something about the carbonyl but held back, and really the scaffolding just, I suppose, gave that little bit of confidence. So how much was about awareness, how much is it about teaching that is actually responsible for a mechanistic issue?
I think what I can't say a lot about the confidence, but we can see that with the scaffold, the one decision-making process of students, or just taking one variable and going further with that, the scaffold helped to slow the students down. Kind of, okay, you don't have to make the final claim right now. We just focus on the structural difference, the change, and then you just fill out the sheet, and then after all you want to do, then you make the final claim. So it's kind of, it slows down all the process. And what we see without the scaffold, in Marie's example, she was thinking, okay, I already found a difference and that should be enough, so just go ahead. I know that there's something else, but so kind of to move on and answering the question. And the scaffold helped the students to slow down. And we also have evidences in the interview or in the transcript that the students were kind of surprised that they could answer these case comparisons with the scaffold, kind of as a help, as a tool to not overlook any variables that are in the problem. So that kind of could also increase their competence, because they had not so many problems to fill out the boxes of the sheets, but they had problems without the scaffold, because then they were overlooking variables and effects that they could formulate with their prior knowledge, but they haven't thought about it.
Yeah. So I mean, it seems to me these scaffold sheets are actually quite useful classroom activities.
Yeah. I mean, you should really, frame what you mean with change. So this was a thing that we had time to explain what we mean with the change in the interview or in the teaching experiment, but maybe you can think about verbalizing that a little bit differently. But we have submitted a paper that explains the scaffold, and there's also the instructions that we used in the interview to scaffold the students. So so all of the people that are interested in using maybe or trying out that scaffold in their classes, I refer to the publication, and then there's tons of information about the prompts that we used.
Great. Yeah. Well, what I might do is put those links on your page on our website, so that people who are looking at the recording of this talk can see those links and click through when they're available.
Yeah.
I think Ira has just posted in a comment. She's sort of your sidekick. She's posted in some description about one of an earlier question, so people can read that. But as we are pretty much over time, I will just conclude by thanking you very much, Nicole, for your time and contribution, and for dealing with the rather awkward and cumbersome software that this webinar system is. But it was a really fascinating talk, I think, both in terms of how you explored this from a methodological point of view, but also the output and the information. I mean, I think a lot of the questions really highlighted the fact that this is such useful information in terms of teaching practice. So thank you very much for your contribution. And just
thank
to
you for
flag,
the audience.
Just to flag to everybody that next month our next speaker is Ginger Schultz from University of Michigan, and she'll be talking about writing to learn. And we'll make the time available in the next week or so. So please do register, and just be aware that if you're joining us from outside of Greenwich Mean Time, that the daylight time changes at the end of this month. So just make sure you did the conversion properly. So I'll leave it there, and I'll put the recording online as soon as the